All right, everybody. In this next section of material, we are going to take our look at graphs just one step farther and talk about something that's called concavity. Concavity, Concavity. Okay, so concavity, I've mentioned it a time or two, but basically it's a look at whether the overall slope of the graph is increasing or decreasing. Okay, so let me just give you a quick little thing. If it's a happy face, we'd say this is concave up. Okay, so if it's looks like an upward facing parabola, that's concave up. And if it looks like that, a downward facing parabola or a frowny face, that is concave down. Okay, so those are the two, like just kind of thinking about it. That's how it's going to look. The problem that people have here is that you can be, for instance, concave up. This is if I split this picture right here in half. That guy is still part of the concave up graph, right? But what is happening as I move from left to right? Is the graph increasing or is the graph decreasing? And I hope you see that the graph is going down right there until I get to the vertex there. So this is decreasing. So it bugs people sometimes to think, oh, the graph can be decreasing while it's still concave up. So on the other side, if I look beyond the vertex, that's still concave up, but what's happening here with the graph? It's concave up and the graph is increasing, right? Okay. Similar thing going on here with concave down. We can tell it changes directions right here where the vertex is. So this is a concave down graph, but if I look at the left-hand side of it, on the left-hand side of that vertex, it's increasing. The graph is increasing right there. So yes, you can be increasing while still concave down. And if we look at the right side, yes, we can be decreasing and still be concave down. So there's different pieces that go on here. And I'm literally going to draw right here and say this piece is decreasing, right? But it's concave up. This piece is increasing, also concave up. Okay. And then here, if I split this one, this piece is increasing because it's going up from left to right. But we can tell it's in that concave down graph. Okay. And the piece on the right, as I said, we're decreasing, but still in that concave down graph. Okay. So there's four different things could be happening here. And it's like this mixture that's going on. Well, how did we tell? So here's some questions. How did we know if the graph was increasing or decreasing? Okay. And we just covered this in the last section of material. Okay, how do we know if the graph is increasing or decreasing? And so in my head, I'm hearing you say, well, hopefully we're looking at what? The first derivative, Dr. Webster, and that's right, f prime of x, right? So the first derivative was what told me if my graph was increasing or decreasing. And just as a side point, remember, if you want to know a particular point on the graph, you actually put the whatever x value you're looking for into the original to get the point on the graph, right? This is the actual slope of the line. So is it a positive slope? Is it a negative slope, right? And so we said if it was a positive slope, it was an increase. If it was a negative slope, it was a decrease. So that should be a reminder from the last section of material. Okay. So that's my little question for you about this. How do we know if it's increasing or decreasing? Well, that's all based on the f prime of x. And real quickly, what did we do? We found the derivative. We set it equal to 0. We solved for x. We found our critical values. We put it together in a sign chart. We picked test points. And that told us that the sections or the regions of the graph where it was decreasing or where it was increasing, where it was increasing or where it was decreasing. That was all based on that first derivative test, right? Okay, so the really great news here for us about the second derivative is that the process is going to work exactly the same as it did for the first derivative. So in other words, we're going to figure out how to take the second derivative. I'll talk to you about that in a second. And then once we do that, we're going to do the same steps. We're going to take the second derivative, set it equal to 0, solve for x, find my critical values, pick a sign chart, do your test points. All of that is going to be work the exact same way. And it's the second derivative that tells me concavity. So how do we determine concavity? I'm going to have to going to go ahead and say concave up versus concave down. And I just gave you the answer to this. So hopefully you're over there saying, take the second derivative, Dr. Webster. And that would be exactly right. All right. So, and notice that I've got this new notation that I just put in there and acted like you knew it. Okay. So previously we've been working with this guy, f prime of x, and that was first derivative, right? We're used to that notation. And I just threw in this double prime, f double prime of x, which is second derivative. Okay. So if you want to know about concavity, you're going to deal with f double prime, second derivative. Okay. So I've got two little things for us to kind of look at, and we're going to hopefully drive this point home by looking at two different things. So first, let's look at f of x equals x squared. And we're just going to talk about the basic graph of that guy, x and y. And I'm only going to look, sorry. And I'm only going to look over here on the positive side. So in other words, we know if I just take x squared and I don't move it or shift it or stretch it or any of those kinds of transformation, that the positive side looks like that. There's also this piece over here, right? But I'm not dealing with that guy right now. I only want to talk about this side on the right. Okay. So if you'll remember when we talked about slope of a line and tangent lines in particular, we said, well, let's look at a tangent line is one that just barely touches the curve in one spot, right? And so what we had said with the first derivative is if we could find the slope of this tangent line, we can use it to approximate what's going on right here at this point on the curve, right? Okay. So whenever we had that point or that particular graph of a tangent line, okay, that one, it doesn't look too terribly steep, right? And in fact, if we found the slope here between these 2 points, over 1, up 1, the points are 1, 1, and 0, 0, right? If I use just these 2 points right here. Okay, so as a matter of fact, go ahead and do that. Find the average rate of change, AROC, between 1, 1 and 0, 0. So we know that we go the change in y's, which is 1 minus 0, over the change in x's, which is 1 minus 0. So that's a 1 over 1. So my slope there between those 2 points, if I was doing a secant line, I'm sorry, that slope right there before the secant line would be a 1 over 1. Okay. If you wanted the instant rate of change here for this one point for the tangent line, you'd have to find IROC, right? Instant rate of change. Okay. And we know to do that, we're going to find our difference quotient. We're going to take the limit as h goes to 0, and we're going to do all that stuff we did in the last few weeks, right? Where we take in derivative by hand and all that stuff. So what I want to do is think, okay, what if I went just a little bit farther over here to the right? So I'm going to kind of exaggerate it a tiny bit. 2, 4 would be my next point, right? I'm sorry, this one's a little bit far off. But 2, 4, 2 squared is 4, right? Because we're dealing with x squared. Okay, so if I put in x equals 2, I get the point 2, 4. Okay, so up here, if I were to draw a tangent line right here, just compare these two lines right here. The slope of this line is relatively shallow. We know that the slope of this line is m equals 1. That was the secant line. Here's the tangent line. That one is still relatively shallow, but what do we think? Here was m equals 1. Do we think the slope of this tangent line is steeper than that? I do. I think this line is steeper, okay? And then when we moved here farther to the right to the point 2, 4 and put my tangent line that there, what do we think about that one? Is it steeper? I think this is definitely steeper. In fact, if it was just a little bit more vertical, we'd have a vertical line and we'd be in trouble, right? So steeper, even more steep, right? Okay, so the idea here that I'm getting at is as I go along here and I'm looking at these tangent lines, we know that the tangent line represents the slope at that point, but what's happening to the slopes of my tangent lines? That's what I want to know. And as I look at this, my slopes of my tangent line are getting steeper and steeper, right? So these slopes here are increasing, if that makes sense. So that's really going to be important because when we look at the second derivative, first derivative was the change on the graph. Second derivative is the change of the slope. Okay. So remember, IROC was tangent line. Sorry. I didn't write that down. Okay. So, but the second derivative is the change in the slope of the tangent line. And here we see this is definitely an increasing situation, right? Okay. So when we're looking at concave up stuff, we've definitely got an increase going on. All right. On the other side, let's look at f of x equals square root of x. Okay. And again, just a quick sketch of this graph. Okay, not to do anything, crazy with it or anything like that, but it starts right here at 0, 0, and it looks like this. Okay, that's the square root of x. Remembering that this is only the positive square root of x. If I had the negative square root of x, it would be over here. And then we know, of course, that would not be a function. That's why we usually, when we're dealing with square root of x in the graph, we usually only deal with the positive side of him. Okay, but let's talk about these tangent lines. Okay, so here, if I put a tangent line right here, what do we think? I think that one looks pretty steep. It looks almost like that one, right? It's not quite vertical, but it's pretty steep. Okay. So let's come out. We've got the point 1, 1. And if we put a tangent line, I know my scale is never right. I'm sorry. Okay, if I put a tangent line like that-ish, what do we think? Okay, it's still going up, but it's not going up as quickly as this one, right? This one was the steepest. This one's a little shallower. And then let's come out here whenever we're just basically doing this backwards from what we had before. Whenever I come way out here, I've got the point, hey, if you put in a 4 here and take the square root, you get 4, 2, right? So right around in there somewhere. Again, it's just a sketch. All right, draw that guy's tangent line, and hey, look, this is almost flat, right? This is almost a horizontal line. So what do we think about those slopes? Okay, if these were increasing, slopes were increasing. That's what I said a minute ago, right? Then what do we think about this? This was really steep, not so steep, really shallow. Okay. I think the slopes over here are decreasing. What do you think? Does it look like that? Really steep, not so steep, shallower. And again, remember we always read our graphs from left to right. So as I go along, it was really steep, not so steep, really pretty shallow. And if I did one way out here, that one would be probably fairly horizontal, right? Okay. So this is telling me the slope is decreasing. So in other words, f prime of x is decreasing. So the second derivative allows me to look at the changes that are happening in the slopes of the tangent lines. Okay, that's called concavity. Okay, another real quick thing I want to point out, and I actually just saw this not too terribly long ago when I was reading in your textbook, and it was an interesting thing. And it said if you have a concave up curve, that curve is always, the graph is always above your tangent lines. I find that really interesting. Even if I had drawn my tangent lines over here on the negative side, okay, where this was decreasing but also concave up, okay, the tangent line would still be below the graph, right? The graph is above, okay? As opposed to over here, where the curve was here, the graph was here, the graph here is below the tangent lines. And that has to do with the way the concavity works, right? Okay, so it's kind of an interesting little point that's how we can tell it. All right, so what are we talking about here? We're talking about taking the derivative of the derivative. We're going to find out where our f prime, or our original first derivative, is decreasing, or I didn't write it over here, slopes are increasing. That means f prime was increasing, right? Okay. So by taking the derivative of the first derivative, that's going to give me the second derivative, I'm going to find out where are those original derivatives growing or decreasing, increasing or decreasing. All right, that's the idea here. Okay, so let's get a little definition here. The second derivative of y equals f of x is given by f double prime of x. That's that notation I threw at you a minute ago, which is the derivative d dx of f prime of x. Okay. So we're taking the derivative of the derivative, or y double prime. Okay, you might see it said that way. There's other ways to do it, but if you went into a more advanced calculus class, for instance, you might see something that was like d squared over dx, that kind of thing. They have some weird notations that come up. We're not going to use any of those. We're going to use the double prime notation here, or double apostrophes in either one of those cases. And yes, you can use it with the f prime, or you can use it with just the original function was y, right? So we can use y double prime as well. Okay, so what in the heck are you talking about? Okay, so what we're going to do is we're going to take the derivative of a function, and then we're going to take it again. I'm going to say take the derivative of the derivative. That's what we're after here. Okay. It sounds a little crazy, but it's actually most people actually are like, oh, I can do this easy because y'all are by now hopefully really good with your shortcut rules. And a lot of these are going to be shortcut rules. There will be a few where we have to employ some product rules and stuff like that. But even those are shortcuts. We're not normally going to do this derivative by hand. Oh, excuse me. So here's our example. Find the second derivative. We'll do one together and then I'll let you work a couple and see how you do. Fine, I cannot write today or speak. I'm sorry. Find the second derivative. F of x equals h to the third plus 5. Oh my gosh, I can't talk today. X to the third plus 5x squared. I'm sorry, you guys. All right, so what are we going to do? First thing we're going to do is take the derivative of this guy, f prime of x. And we know by now our shortcut rules. We're going to multiply the 3 out in front, and we're going to subtract 1 from the exponent, right? So the derivative of the first term here is 3x squared. Okay. And then just keep on going. It's a plus. And this guy is also a power rule. So I can just multiply that 2 out in front. I've got a 5 times 2 is a 10x, and then subtract 1 from the exponent there. It becomes a 1. I don't have to write the 1. You can if you want to. All right. So that's the first derivative, right? Everybody should be hunky-dory with these by now. All right. But that's not what we're asking for. We're asking for the second derivative. So this is where I'm going to take the derivative of function. Just did that. Check. Take the derivative of the derivative. Okay, so from here, starting from this point, take the derivative of this derivative. It's actually, like I said, most of you are going to be like, oh, score, I can do this. So you're just going to do it again, right? This is a nice, pretty polynomial function going on here. We can use our power rule, multiply the 2 out in front. 6x, subtract 1 from that exponent, it's x to the first. Plus, be careful with this second one because whenever I multiply out in front, 10 times 1 is 10x. Whenever I subtract 1 from the exponent, that becomes x to the 0. Or many of you, hopefully by now, just know, hey, when I saw that 1, this is going to go away. That becomes a 1, right? X to the 0, anything to the 0 is a 1. Anything to the 0 power is a 1. Remember that? So that's a 1. So that's just 10 times 1, so that's just 10. So this just becomes 6x plus 10. Okay? So that's what I meant by most of you are going to be like, oh, I can take the second derivative. That's pretty good. All right? So hopefully that made sense. If you need to rewind or do that again, that's fine. Here's one for you to work for. Okay? Find y prime, double prime. Okay, sorry, double prime. If y equals 4x squared plus 3x minus 8. Okay, go ahead and work on that. If you want to push pause, you can. I'm going to go ahead and do this. The first derivative is power rule, right? So 8x, what happens here? 2 minus 1 is 1. I can put the 1 there or ignore it if I want. Okay, the derivative here, this exponent is really a 1. So when you go to do that power rule, remember it's a plus. 3 times 1 is 3. That 1 minus 1, that's a 0. X to the 0 is a 1. So 3 times 1, or I can just write 3. And what about this minus 8 sitting out here? That is a constant, and we know the derivative of constant is 0. So that just goes away, right? So I just get 8x plus 3. Okay. Hopefully you did that, no problems. That was my first derivative. The problem did not ask for first derivative. It asked for second derivative. So I'm going to keep going. Okay. This is my first derivative. What's the second derivative? Y double prime. Okay, the exponent there is a 1. 8 times 1 is 8. X to the 1 minus 1 is 0. X to the 0 is a 1. That's just 8 times 1. Plus, what about this 3 guy? He's a constant, so the derivative of a constant is 0. That's just an 8. Okay. Are we okay with that? All right, and one more for you to work on. Let's see what you get. Find h of x, h double prime of x, if h of x equals 8x plus 10. Okay. So if you need to pause for a second, this one is not really tricky, but some people may see it as a little bit tricky. So we're going to think about it for a second. H prime of x is what? Take the derivative of that. You get 8. That's a 1 minus 1. That's a 0. This derivative is a 0. So I've just got 8 x to the 0, but that's just a 1. So what do we think about that? H prime of x is 8. Then h double prime of x is, again, it's not meant to be tricky, but it is a weird thing. Is everybody getting 0? Yeah. Okay, because that was a constant, right? So when I take the derivative of just the constant, I get just a 0. And there's no variable part left to it for me to have anything other than the 0 there. So it's just a 0 and we're done. Okay. All right, let's do one a tiny bit harder here because those were all nice, pretty polynomials. And we know, hey, they're not always nice, pretty polynomials. So here's your next example. Find the second derivative. If f of x equals x plus 5 times 3x squared minus 2. All right, now we're getting to the nitty gritty, right? Hopefully you're looking at that going, ooh, that is not a pretty polynomial anymore, right? So it's not, and I look at this and I go, hey, this kind of looks like this guy's a function and this guy's a function, and they're being what? Multiplied together. That's right. They're being multiplied together. So when I go to do this, and I really want you to get to where you can just look at these things and say, oop, that's a product rule. Okay, hopefully you've done enough of these homeworks over and over and over again. We're going to find out soon. We're going to be doing practice problems for the exam, and you're going to have to look at these things. I'm not going to say use the product rule. I'm not going to do that. Okay, you're going to have to look at it and go, ooh, I'm going to say find the derivative. Okay, and you're going to look at it and go, ooh, that's a product. I need to use my product rule. And I'm not going to give you hints on that. Okay, so you're going to have to know coming in. Okay, so the derivative of something that's a product rule, remember, it's first, just like it is, write it down, times the derivative of the second, so be careful with this. It's 2 times 3 is 6x, 2 minus 1, that's just a first. And this guy is a constant, so that would be plus a 0, but we don't care about that. So first times the derivative of the second, first times the derivative of the second, plus the second guy, write him down just the way he came in. Okay, no changes, just the second guy times the derivative of the first. Well, this is the first guy. What's his derivative? Okay, this, what's out in front here? There's a 1 out in front, and there's a 1 in the exponent, right? 1 times 1 is just 1. X to the 0 is just 1, so that's a 1. What's the derivative of the constant? That's a plus 0, so that's just 1. Okay. There we have that. So I need to make this a little bit prettier, and we can do that. This 6x needs distributed through. So 6x squared plus 30x. And then here in the back, this is all times 1, but who cares? I've got a plus 3x squared minus 2. And I can combine these like terms. So I've got 9x squared plus 30x minus 2. And hey, look, this thing that was a product rule turned into a very nice polynomial, right? Okay, so that's really cool for us because we're not done, right? We've only found first derivative. We want second derivative, okay? So in order for me to go to that second derivative, I now need to come back here and take the derivative. Oh, I'm sorry. The derivative of the derivative. So I need to work off this guy. So here we go. 18x to the first power, right? I don't have to write it. I'm just saying 18x. And what's the derivative of 30x? Plus 30, right? This is x to the first. 30 times 1, 30. Subtract 1 off there. That's a 0. That goes away. So 30. And then what about the derivative of that? That's a plus 0, but I don't care about that. So there we go. There is my second derivative. Okay. So sometimes these product rules, quotient rules, chain rules, things like that, sometimes they work themselves out very nicely. Sometimes they can become, oh, excuse me, even more complicated. So sometimes that's just a pain in the rear. Okay, so FYI. All right. Let's look at the original guys that I was looking at before. So here we go. I've got x squared and square root of x. So here's what I want to do. We know those derivatives. So I want to go, we know the original functions. So I've got f of x was x squared for one of them. And over here on the other side, I had f of x was square root of x. Now I want to go back to these two because we actually already know exactly what's going on with these, right? Okay, this one is always concave up. This one is always concave down. So we know what's going on, and I want to look at that and see what the heck's happening when I take the second derivative and look at that thing, okay? So what we just did a second ago was not actually using the second derivative test. We were just finding second derivatives because I wanted you to have a little bit of practice with finding the second derivative before we actually drop into what the heck is the second derivative test, okay? So we're going to get there, but we haven't gotten there yet, okay? So I want to do what we just did. Find the first derivative, this guy. Okay, so I think the first derivative is 2x. Find the second derivative. I think the second derivative is 2. And what we're going to do here is we're going to look at that second derivative. Now, this one's actually kind of nice because it's 2. And all you're going to do here is the same as whenever we were looking at first derivative, is you're going to tell me, is that a positive or negative? Well, this one's always positive, right? 2 is always positive. All right. So as I look at that and I go, oh, 2 is always positive, then I know that the second derivative is always positive. This is always concave up. So let me put that into writing. We had, let me say, 4, x was greater than 0. Okay. The f double prime of x was also greater than 0. It was positive. That's what this means. We were positive. And again, oops, where did I put it? I'm sorry. Again, I was only looking at the positive side of this guy, right? We showed it for the negative also, but I'm just putting in the positive side. So when we're looking at the positive side, our second derivative is always positive, excuse me. And therefore, because the second derivative is a positive, f prime of x, the original derivative, is increasing. Okay, So because the derivative of the derivative is positive, we know that the slope of the tangent lines is increasing. Well, we already knew that, right? We saw that. The slope of the tangent lines, this one was shallow, that one was a little more, that one was the steepest, right? So we already knew the slope of the tangent lines was increasing. This just helps me out. And what I find is that, so when f double prime of x, double prime of x is greater than 0, the original function is concave up. That's what it's telling me. Okay. And in this case, it happens to be true everywhere because this is just a nice parabola, right? It looks like that. It's always concave up in this case. All right. But that's not always the case. And that's where my second derivative test is going to come in just a tiny bit of time. We'll see it. But over here, let's do this one. Now, before I take this guy's derivative, I'm going to rewrite this. Use your flower power, whatever you have to do. It's x to the, what's the exponent? 1, and that's the power on top. And what's the root? The index here is a 2. That's the root on the bottom. So this is really x to the 1/2. And seriously, you've got to be able to rewrite these exponent-wise that quickly. Okay, x to the 1/2. So that's my original function. So if f of x equals x to the 1/2, find f prime of x. Okay, 1/2 x to the, remember you're subtracting 1. 1/2 minus 1 is a negative 1/2. Okay, there's your first derivative. And then go ahead and find your second derivative. Okay, be a tiny bit careful with this. So whenever I multiply this out in front, let me write it first. I've got negative 1/2, because that was the exponent, times the 1/2 that's sitting out in front. X to the subtract 1, well, I've got a negative 1/2 minus a 1, or if you need to, you can say minus 2 over 2. That's a negative 3/2. That's my exponent, right? And then hopefully we can do this multiplication. Negative 1/2 times negative 1/2 is negative 1/4. X to the negative 3/2. There we go. All right. Let me play with this just a tiny bit because sometimes we don't like this. Remembering that the negative exponent happened whenever I move something to the top. So I can rewrite this negative 1/4 x to the 3/2. Put that x to the 3/2 on bottom. Make the exponent positive. And then if you wanted to, you could go ahead and rearrange this so that it's a square root of x to the 3rd. You could put it as a radical if you need to. Okay. But the interesting thing here is what happens. I've got the square root of x to the 3rd, and we were only dealing with, here was my graph. Again, we were only dealing with positive x's here, right? X was greater than 0 because I only dealt with this half, the positive half. Okay, so what we've got going on here for x is greater than 0, what are we seeing? Okay, earlier when we had x was greater than 0, we saw that the double prime of x was also greater than 0. But now I'm looking at this guy going, okay, let's think about this. Let me rewrite this one more time just in case people are having a problem with this. Square root of x to the 3rd, right? That's what this is. Use your flower power. Okay, so I take a positive number and I cube it. Well, that's positive. And then I take the square root, that's still positive, and I multiply it by a 4, that's still positive. But on top, I've got a negative 1. Negative 1 divided by some positive number. What do you think? I think it's negative, Dr. Webster. And I agree, it's negative. So f double prime of x here is less than 0. Okay. Always, whenever we're dealing with these, x's are greater than 0 here. So now I've got something that's less than 0. That tells me that, so f prime of x is decreasing. Okay, here it was increasing, there's decreasing. Well, hang in a minute. We said that already. The slope of the tangent lines, this is really steep, a little bit shallower, a little bit shallower. The slope is decreasing, right? I even wrote it right there. Slopes were decreasing. Okay, so the f prime of x was decreasing, and that means the original function is concave down. That's what that means, down. And that is going to be how we kind of take these things and look at them and go, oh, what the heck's happening inside of there? Why are we seeing what we're seeing concavity wise? Either growing or not growing, decaying, that kind of thing. And that's going to come down to my first derivative test. Okay. I'm sorry, my second derivative test. Not let me not lie to you. Okay, so what we have here is kind of a chart. Okay, so second derivative test tells me regions of the graph that are either concave up or concave down. Okay. And I'm going to say, as long as there's no weirdos that happen, because we know there can always be something unusual that happens. Like, what if the graph was just a constant graph or something like that? Well, then it's not concave up or concave down. It's neither one. So then we'd have to deal with that. Okay. So it would happen. But second derivative test tells me regions where we're going to have either concave up or concave down. So what's going to happen? We're going to have something that looks like this table. We're going to have the second derivative, and it's either going to be positive or it's going to be negative. Okay. And we're really just looking at that. Okay. And then we're going to have a first derivative. Okay. We already took that one. And we're going to know that it was increasing or decreasing based on the first derivative test, right? Okay. So I'm sorry, not still the second derivative test. So what I'm saying is we found that our double prime, our second derivative was positive. That tells me that my first derivative was increasing. If the second derivative was negative, that tells me that the first derivative was decreasing. Okay. And then what does that tell me about my original graph? Okay. Well, if the slope of the tangent line is increasing, then that means we're going concave up. And if the slope of the tangent line is decreasing, then our original graph is concave down. Okay. And so then we're going to deal with, okay, is the overall graph increasing or decreasing? Oh, I'm sorry. But we'll have pieces of the graph that look like this. Concave up, we'll have these two pieces that would put together a parabola for me. Concave down is these two pieces that would show me that upside down parabola. Okay, that's what we're talking about. So what I want you to know or make sure of that you know is, so special note, concavity is not the same thing, not the same as rising or falling, right? If the graph was rising or falling, if we're trying to determine if the graph is rising or falling, what derivative are we going to use? The first derivative, right? So that's not the same thing at all. In fact, we can have, like I said here, these four different pieces. So we can have this piece, we can have this piece, or we can have this piece, or we can have this piece, right? Those 1, 2, 3, 4, 4 pieces. 2 pieces of the upward parabola, 2 pieces of the downward parabola. So talk to me about what's going on with this one. Think about it. Okay. Is this graph rising or falling? Falling, Dr. Webster. Okay. Is this graph rising or falling? Rising. What about this one? Be careful. Read left to right. Even though the arrow is pointing this way, we always read left to right. What's going on? It's rising. And what about this one over here? Falling. Okay. Always left to right. Okay. So that's what's going on as far as rising or falling. But what do we know about this one's concavity? Both of these are concave up, right? Absolutely. So these two pieces go together, and inside of concave up, you can have either a rising piece or a falling piece. And then what about these? I said these make the downward parabola. So these are concave down. And again, depending on what part of the parabola I'm looking at, we can see it's either rising or falling. Okay. So what we see is we actually need both of these derivative tests. Okay. The first derivative test told me where the graph was rising and falling. The second derivative test is going to tell me if it's concave up or concave down. So we need both of those pieces put together to help us out here. That's what's going to happen. All right. That is how my second derivative test is going to work. How are we actually going to implement it? Just like the first derivative test. So without further ado, we will have an example. Okay. Determine intervals of concave up and concave down. That's about what my math lab is going to say. Oops, up or down. Determine intervals of concave up or down, and my f of x is x to the third. All right. So this one's fairly straightforward, I think. Go ahead and find your first derivative. Go ahead and find your second derivative. Hopefully you can do it that quickly because these are easy, quote unquote, polynomials, right? This was a very straightforward one. So I think my second derivative is 6x. All right. So remind me, what were my steps for the derivative test? We did first derivative test, but now we're doing second derivative test. So find the second derivative. Okay. Which you're going to have to find the first derivative before you can find the second derivative, because the second derivative is the derivative of the derivative. So find them both. Okay. Number 2, set f double prime of x equal to 0, right? Just like I said, we're going to do this just like we did with the first derivative test. So let's do it. Here's my double prime, 6x equals 0. That's what that looks like. All right. Step number 3, I said solve for x or whatever your variable is. So let's solve for x. I'm going to divide by 6 on both sides. X equals 0. That's solving for x. And then step 4, make your sign chart. By the way, what is this? Critical value, Dr. Webster. That's right. So you set it equal to 0 and solve for x and find your critical values. In this case, I only have one critical value. Solve for x, and step 4 is sign chart. If you want to make a fifth step, but I think it's part of step 4, don't forget about your test points, right? So I've got my critical value. I need my sign chart. Remember, that's just a number line. So I'm going to put my x value there is 0. That's my critical value. And I found that sorry, I need to put my f of x and my f double prime of x. Okay, on the last one, when we did first derivative test, we only had one prime, right? Now I have both primes. Okay, so I found that x equals 0, remember, by forcing that thing to equal 0. So this is the spot where I'm going to have a 0 value there for my second derivative. Remember also from first derivative test, we could have a does not exist there if we had some weird thing going on, like these were vertical asymptotes or something whenever we were doing first derivative test. Oh, excuse me. We saw we might have some does not exist cases. So certain things like that might happen here. We'll see a situation where weird stuff happens. So we'll talk about that in a minute. Okay, but for right now, I only have one critical value. It is x equals 0. Okay, and it is a 0 in my second derivative. So remember, I need some test points. I'm going to use +1 and -1. Okay. And we are going to test them in the derivative, right? The second derivative in this case. So my second derivative was 6x. So f double prime of x was 6x. So f double prime of 1 is 6 times 1. That's a 6. Again, just like before when we did first derivative test, I don't care the value. I care that it's a positive. So this guy is positive, 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 positive. Okay, so what does that tell me about what's going on here? This is my dividing line, right? What does that tell me about what's going on here in my f of x? Positives was concave up, right? Absolutely. So remember, you find something out with the derivative you're working on, but then that tells you something about the graph of the function. So you've got the positives that's on your sign chart, but figure out concavity based on that. Okay. And then what about whenever I put in f double prime of -1? 6 times -1, that's a -6. Again, I don't care about the -6 part. I care about the negativeness of it. And remember, I only have to pick one point, one test point on this section of the graph, because if you'd pick -300, you would still be getting a negative value here, right? And then if the positive told me that the graph was concave up, then the negative tells me that the graph is concave down. Okay. So, interestingly enough, let me go ahead and give you the intervals of concavity here because it asked me to determine intervals. So, I've got concave up from here where I started at 0 all the way to positive infinity. Is everybody okay with that? All right. And I've got concave down. Again, remember we always read these intervals from left to right. So it started way out here at negative infinity and came up here to where I hit 0. Okay. So that's my actual answer to this question because it asks for intervals. But also, I have an interesting thing happening here. So let's think about this. This guy was concave down. And at this particular critical value, it turned into concave up. So what's happening here is I had something concave down, and it turns into something that's concave up. Okay. Does everybody agree? This is down. That's a negative frowny face. This guy's up. It's a positive. Okay. So something like that. It's probably not as drastic as this. In fact, I know it's not because the actual graph, I'll show it to you in a second. But it's changing that concavity. And what we call that whenever it changes concavity, if a graph changes concavity, we call the point where it changes a point of inflection. And I think I've already used this terminology. Think I used it when we talked about first derivative tests. Sometimes we might get a point of inflection. This is different from in the first derivative test when we had a change in direction. Remember, a change in direction could have been a maximum or a minimum. It could be some weird does not exist thing, right? But most of the time we're looking at maxes and mins when we do that. But this isn't a change in direction. This is a change in concavity. So it's just a flexion point, a point of inflection. It's just a bare minimum change, okay, in direction. And in fact, we know this original graph was x to the third, right? Okay, so let me see if I can get my calculator to graph me an x to the third. Okay, there it is. And we can see that this point of inflection right there at x equals 0 is very minor, but indeed this is a downward parabola right there, or a part of it, right? And that on the right-hand side is a part of an upward parabola. So we're just piecing it together, and sure enough, it did change concavity, and that guy right there, x equals 0, is a point of inflection. So my critical value in that case turns into a point of inflection. All right. Okay. So that's what I mean by the process is the same as when we did first derivative test. All the steps are there. And I would like for you guys to do f of x equals 4x to the third minus 6x squared. Sorry, I'm just reading my own handwriting. Plus 9x plus 1. All right, go ahead and see if you can do that. If you want to pause this, you can. I'm going to run through it real quickly. If you pause and then come back, we can do it together. All right, so as I work through this, I think I've got f double prime of x is 24x minus 12. Okay, so hopefully you got something that looks like that. That's my step 1, and then I'm going to go to step 2, which is set this guy equal to 0. So 24x minus 12 equals 0, and I'm going to solve for x. So 24x equals a 12. Divide by 24 on both sides. I get x equals 1/2. Okay. And then step 3. Oops, I already set it equal to 0. This was step 3. Solve for x. I got that. And then step 4 is my sign chart, right? So here I go. I've got my sign chart. My critical value here was 1/2. It was indeed a 0 on the derivative. I set it equal to 0. I forced it. Okay. So I need some points on both sides of 1/2. I know that 1/2 is slightly bigger than 0 and slightly smaller than 1. So I'm going to pick 0 and 1 as my two critical values and as my two test points. And I'm going to plug those in to the original f double prime, which was right here, right? So, 24 times 0. Let me put it here, f double prime of 0. Oops, sorry. 24 times 0 minus 12. Okay, so 24 times 0 is 0, minus 12 is a negative 12. So over here on the left-hand side, I'm getting minus, 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 minus. And so I know that this graph is concave. What do you think? Minus, minus, minus. Down. Good. I hope you think it's down. Concave down. Okay, and then what about over here on the the right-hand side of the 1/2, where I picked 1 is my test point. 24 times 1 is 24, minus 12 is a positive 12. So I'm getting positive, positive, positive. And again, it doesn't matter if you pick the 1 with me. You could pick 5 million, and you would still get a positive. And when we get a positive on the second derivative, we know that means my original graph is concave up. Okay. Is that all right? Okay, so did we have a change from concavity, from concave down to concave up? Yes, we did. So now we know x equals 1/2 is an inflection point. Okay, now, everybody all right with that? So I'm going to use that definition. And it doesn't always have to be down to up. It could change from concave up to concave down. That's still an inflection point. So here's my question. How do I know, by the way, how do I know what that particular point is? X equals 1/2 on the graph. I've got the X value. How do I get my Y value there? If I wanted to write it, like I'm thinking I might want to write this as the point 1/2 for the X value and then some Y value. So how do I get this Y value is my question. And I hope in your head you're thinking, well, you're going to go way back up here to the original function, not the first derivative, not the second derivative. We're going to go to the original function because to get a point on the graph, to get points on the graph, we use the original function, right? Use f of x. All right, so just be aware that's how I would figure out exactly what that point is. But I'm cool if you want to say x equals 1/2. What I'm not cool with if you just say 1/2, right? And I think I've made that mention before, and I think when we've tested before, like some people have lost points because as I just said 1/2, it's not sufficient to just say 1/2. I need you to say x equals 1/2. Or put it into point notation and find that y value for me if you want to do that. That would be okay. Okay, let's do another one. We're going to use some weird stuff now. It's always fun when we have weird stuff. Okay, so all the stuff we've had so far was stuff where we said, oh, we're good because we can set that equal to 0 and solve. So let's see what happens when weird stuff happens. So original function is g of x equals 1 over x. Okay, so if you're not aware of this family of functions, go and pop it on your calculator or something like that. But hopefully you know that this particular function looks something like this. And we called that a piecewise function when we dealt with this. We have both a vertical asymptote and a horizontal asymptote. We covered all of that whenever we looked at rational expressions, right? I'm going to go ahead and rewrite this x to the negative 1 because I want to work like with this as if it was a power rule on a polynomial function type thing. But just realize this isn't actually a polynomial function because this was rational, right? This was piecewise. My graph is piecewise. The function is a rational function. Okay, so what does that tell me? We have a real problem here at what? X equals 0. In fact, x cannot be 0. If you look right here, you can't divide by 0, right? So that's a domain issue. And guess what almost always happens here? Where do you think my critical value is going to be? My critical value is going to be there at x equals 0. Absolutely it is. All right, so let's see how we do with this. Let's take the derivative. G prime of x is equal to, bring this guy down in front, -1, x to the, be careful with those negatives, -1 minus 1, that's a -2. So this is negative x to the -2. That's my first derivative. I need second derivative. Okay, -2 times a -1 is a +2, x to the, let's be careful again here, -2 minus 3, -2 minus 1 is a -3. Okay, so that is my G double prime, or some people want to see it as 2 over x to the third. Those are equivalent. I don't personally care which one you use. Sometimes one form is easier to work with than the other, but we can definitely see here, hey, our problem is going to be, again, here on the bottom, we can't divide by 0. Okay, so I've got my second derivative, and now I want to, oh, excuse me. So follow my steps. This was step 1. Step number 2 says set this guy equal to 0 and solve for x. So I'm going to go 2 times x to the -3 equals 0. That's step number 2. Step number 3 says solve for x. Okay, I set this up like this because I want to divide by 2 to get the x to the -3 by itself. Okay. And I know that 0 divided by 2 is just 0. And then remember your exponent rules. How am I going to get rid of this raised to the -3 power using my power, my different exponent rules? Yeah, I need to multiply this or raise this to the -1/3 power, right? So that those will cancel out. But when I raise a 0 to any power, what do I get? Just 0. X equals 0. So indeed, look at that. This is my critical value. I already knew it was coming, right? Okay. But just realize, even though we set this equal to 0, it's not a 0 value in this graph. It's a does not exist value, right? Okay. So as I do my sign chart, which is number 4, we're just going to keep in mind x can't be 0. That is a bad spot in my domain. So as I set this guy up, f of x, f double prime of x, this guy does not exist here. Okay. And then you just find your test points, right? 1 and a -1. Stick those into, it's probably easier maybe to stick it in here. 2 over x to the third. F double prime of 1 equals 2 over x to the third would be 1 to the third. 1 to the third is a 1. 2 over 1 is a 2. We don't really care. We care that it's positive. Okay. And whenever I have that, I've got concave up on my f of x, and that's what we like. My other test point is -1, f double prime of -1, 2 over. This is why I wanted to use that format for this piece, because I can put the -1 to the third on the bottom and it feels more comfortable to me than raising a -1 to a -3rd power. So I just flipped it to that. And we know, oh, hopefully, that a negative number to an odd power is also a negative number, but just in case, -1 times -1 would be a +1. And then a +1 times -1 would again be a -1. This is a -2. And again, we just care that it's negative, and that means that on the left-hand side of my critical value here, I have concave down. Well, let's go back and look at this graph. Is the piece on the right concave up? Yeah, it kinda looks like, "Hey, you could still be part of the parabola, right?" Is the piece on the left concave down? Sure enough, if I just did that, I'd have the concave down parabola. So yes, this second derivative test stuff is indeed telling me what I thought I would see, and that is lovely. Okay. So you're going to have to play with this a little bit, but honestly, I feel like after doing first derivative test, hopefully the second derivative test feels pretty comfortable to everybody, and you can go from there. All right. Let me know if you have any questions about your homework, and I'll see you later.